class, we are going to see a concept of sum of two random variables In this concept, we are going to find the density function of sum of two random variables, and then we are going to extend it to sum of n number of random variables. Let W is a random variable equal to the sum of two independent random variables. Okay, means let W as x plus y, where x and y are two different random variables. And in the communication concept, x may be our signal voltage, which is of random, and y may be the noise. So your W is signal plus noise. Okay, then the probability distribution function is defined as, we generally represent it with, we'll represent it with for the random variable x, the representation for distribution function is fx of x. Here it is. Generally the representation is fx of x, but here, as this is the distribution function for W, we are representing it with fw of W. So what is this? General representation. If it is fx of x, it is p of x less than or equal to x. It's nothing but, what is W? X plus y. So x plus y less than or equal to W. You can write it as p of x less than or equal to W minus y also. So actually fx of x is p of x less than or equal to x, which is nothing but minus infinity to x fx of x dx. You have this form. Using this, you can write it as integral minus infinity to is, if this is x, the limit is x, but here the term is W minus y, so the limits are minus infinity to W minus y, fx of x dx. And we know from the marginal density concept, what is fx of x? Integral minus infinity to infinite fxy of x comma y dy. Okay, just substitute this in the place of this. So you're going to get integral minus infinity to W minus y, and here another one, integral minus infinity to infinite fxy of x comma y dy, and here it is dx. So what is fw of W? Integral minus infinity to infinite and integral minus infinity to W minus y fxy of x comma y dx dy. You can write it as integral minus infinity to infinite integral minus infinity to w minus y. Yes, if the variables x and y are statistically independent, fxy of x comma y is equal to fx of x into fy of y. They'll separate integral minus infinity to infinite fy of y integral minus infinity to w minus y fx of x dx dy. Now differentiate both sides using Leibniz's rule with respect to w. We get, so see here, d by dw of fw of w is equal to d by dw of integral minus infinity to infinite fy of y integral minus infinity to w minus y fx of x dx dy. And we know differentiation of your distribution function is density function is nothing but your density function. That is equal to, see here w is in the second term only, so the first term is treated as constant, so just keep it like this, fy of y, and now it is d by dw of integral minus infinity to w minus y fx of x dx into dy. Fy of y using Leibniz's rule, and see here it is the differentiation and integration both gets cancelled. By applying Leibniz's rule it becomes simply fx of w minus y dy. What is this? F w of w. So if you observe it carefully, it is nothing but convolution between fy of y and fx of x. Therefore, fw of w equal to fy of y convolved with fx of x. Therefore, what is the conclusion here about the density function? The conclusion is the density function of the sum of two random variables which are statistically independent is the convolution of their individual density functions. Again, you read the conclusion. Density function of sum of two statistically independent random variables is equal to convolution of their individual density functions. You had a small graph that represents this w equal to x plus y see the graph. X and Y. Just keep here W and W. Just join this. This is nothing but X is equal to W. And this is nothing but Y is equal to W. Then what is this line? X plus Y is equal to W. Then the below one, this is all as nothing but X plus Y less than or equal to W. This is 0. So this graph shows the region for which X plus Y less than or equal to W. And this is the line that shows X plus Y is equal to W. To keep the point on X axis, you have to keep Y equal to 0. If you keep Y equal to 0, you will get X is equal to W. Keep here. To get the point on Y axis, keep X is equal to 0, so that you are going to get Y is equal to W. So keep here. You join these two. This line is nothing but your X plus Y is equal to W. Now we'll extend this concept to sum of several random variables. Sum of several random variables. Let x1, x2, etc. xn are the random variables. Now consider first y1 as the sum of x1 plus x2. Then what is Fy1 of y1? According to our previous conclusion, the density function of the sum of two random variables is equal to convolution of their individual density function. So you can write it as fx1 of x1 convolved with fx2 of x2. Fine. Now take another sum y2, that is x1 plus x2 plus x3. Now you can write x1 plus x2 as y1. So it is y1 plus x3. Now what is fy2 of y2? Density function of your y2. Again you have to go for convolution. Fy1 of y1 convolved with fx3 of x3. What is fy1 of y1? From this you can write this total. Fx1 of x1 convolved with fx2 of x2, and here is another term convolved with fx3 of x3. Understood? Suppose if you extend this, go for y3. x1 plus x2 plus x3 plus x4. You can write it as y2 plus x4. Therefore, fy3 of y3 is equal to fy2 of y2 convolved with fx4 of x4. Substitute fy2 of y2 from this. So fx1 of x1 convolved with fx2 of x2 convolved with fx3 of x3 convolved with fx4 of x4. Therefore, the sum of n independent random variables density function is, take it as fy of y, where capital Y is sum of all n independent variables. Means take y as x1 plus x2 plus etc. plus xn. For this, the density function is, what is this? It is the convolution of individual density functions of the random variable xn. So you can write it as f xn of xn convolved with fxn minus 1 of xn minus 1 convolved with fx1 of x1. This is the total convolution. So the density function of any number of random variables, several random variables, is nothing but convolution of their individual density functions.
Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.